Hey everybody, so here's the second page. I think this is the one I gave you guys. I have a lot of worksheets, but I recall I think this is the one that I gave to you. If not, you can do this one as additional practice. Alright, so number 1 says we're taking iron 3 chloride in water, and it wants us to calculate the enthalpy of solution. So that means it's dissolving. So whenever we're doing an enthalpy problem, we always want to have a reaction to look at. So iron is Fe, and of course chlorine is Cl. It says iron 3, so that means it's the 3 plus version. There's 2 choices for iron on the periodic table, and it's important to know which one is which, because when we want to balance these charges, if it was Fe2 plus, it would be a completely different compound, completely different properties. Oops, you can't read that. So in order to get the positive and negative to balance, I need to have 3 of the negative particles here. So to show 3 chlorines, I'm going to put a subscript there. And so when we're dissolving something, it's going to start out as a solid, and it's not actually a chemical change, so I don't write, I'm not going to write water as like a reactant or a product, especially because if you do that, you end up with it as a reactant and a product, so that means it would cross off. Okay, so I'm not going to do that. Also, it's important to know that when we write FeCl3aq, that can also be written as the individual ions that it actually forms. So this is like the net ionic equation thing again. I mean, we get 3 chlorine particles because there's 3 chlorines attached to that iron. So there's 2 different ways to kind of think of this. Both of them will work just fine. So this is an enthalpy question, so back to the appendix. I'm looking under iron, and I see there's FeCl3 solid with a negative 400, so that's going to be over here. And then Fe3 plus is negative 47.69. And the chlorine is going to be, there's no FeCl3aq, so this one isn't as useful with our appendix as looking at it this way. So I'm going to go ahead and use this equation. So that means we got to go find the chlorine values. So chlorine is Cl minus, negative 167.2. Alright, and so delta H is products minus reactants. So here we have negative 47.69 plus 3 times negative 167.2. So that's the energy of our ions, effectively. I'm going to make this a bracket. Minus, there's only one particle here, so minus negative 400 kilojoules per mole. So again, I do the brackets first, then I do this. So here on the product side we have negative 549.29 kilojoules, and it's going to be minus negative 400. So really I'm going to be adding 400. Negative of a negative is a positive. So we're going to end up with negative 149 kilojoules per mole. Okay. So that's question number 1 on this side. 1A, I think. Nope, just 1. This number 2 is similar to what we did in lab in the titration experiment, so experiment 5. So we're looking for oxalic acid, which they give us this value. Oxalic acid is going to be what you get when you take oxalate, C2O4 2-, and combine it with hydrogen, because it's an acid. And that's going to be AQ, again, because it's an acid. And we are reacting it with sodium hydroxide. So that's NaOH, because there's a +1 on the sodium and a -1 on the hydroxide. And so this is going to make water, because it's a neutralization, and a salt. And in this case, the salt is, so double displacement is what I'm doing here. So the H goes with the OH, the Na goes with the C2O4. And this has a 2- charge, so I have to have 2 sodiums to get that to balance. I have 2 hydrogens to react with here, and only 1 OH, so I'm going to have to make 2 waters and have 2 bases. So that's our balanced reaction here. Again, the problem gives us the one that's not in the appendix. So if you look under carbon, there's not going to be an oxalate there. So we're given that one in the problem. It is 35.23. NaOH we have to go look for. It's probably going to be under sodium, so we're going to look there first. Here we go. Oh, NaOH solid and NaOH aqueous. So we have to know whether we have a solution or a solid. I'm going to assume it's just like what we did in lab, and that it's AQ. And over here, this one will be AQ as well because sodium is always soluble. So that would be negative 469.6. That's a big one. Okay, and then we go to oxygen for the water. And so water, we're going to assume it's a liquid, negative 285.83. Because it's not a combustion, that's the logic. Oops, not positive, negative 285. And this one, of course, is not going to be in the appendix either because oxalate's not in there. So I'm going to look in the NIST web book. That's a 4 right there. I don't know why it looks funny. There we go. Did it again. That's still a 4, not a 9. I don't know why it keeps smearing that. But anyway. You can find the web book just by Googling NIST web book. And again, that's where like a lot of our information for the entire nation is sort of housed there. So that brings us here. I'm going to search by name. You could search by formula, but typing it in gets kind of odd because you can't do subscripts and stuff. All right, so here's our sodium oxalate. We're going to the condensed phase thermochem data. And it looks like, oh, they have the heat capacity there. That's interesting. I wonder why somebody needed to measure the heat capacity of sodium oxalate, which is really, really high. It absorbs a lot of heat because it's a solid. Anyway, that's weird. So my secondary source is usually Wikipedia, which is very good for factual information, like physical properties. And you can just search for, all I searched for was sodium oxalate enthalpy. And here it is, negative 1,318. And as always, I'm going to cover my bases by citing, oops. Sorry, I pushed the wrong button on my fancy writing pen thing that I use. I'm going to cite my sources here. Okay, that makes it basically just says that's where I got my information. It doesn't mean I'm responsible for that number. Okay, so that's an important caveat that you should add. So the delta H of reaction is going to be products minus reactants, and so our products here, you know, I think probably that's not the aqueous salt actually, so that might not be the best number. Hopefully you found a better number. We'll use it as our example here, but the important thing is by defining where I got the numbers and what number goes with each chemical species, you can demonstrate understanding of Hess's law even if you don't have the right number in each place. So really that's what I'm looking for. Okay. So that's products. Again, multiplying the coefficient times the enthalpy for each water, minus the reactants, and here we got 35.23, and we have negative 469.6. That's going to be times 2. Okay, so for our products here we got negative 746.34. Again, I don't really care about sig figs for this. These are all theoretical values with lots of inherent error in them. Well, they're actually measured, but we didn't measure it. So there's not really a good reason to worry about the sig figs too much here. Really, I'm most concerned about it whenever it's an actual measurement. Okay, so quite a large value for our reactants here. So we're going to take negative 746.34 plus 903 is what that's going to be. Okay. You can talk for a second, Genevieve.
Okay. I'm gonna make something on this one now.